In this session, we'll see about auto transformer and a three-phase transformer connections. Come to auto transformer. The purpose of auto transformer here is it converts fixed AC signal into variable AC signal with the same frequency. The variable AC signal or AC voltage is nothing but the step down levels only we can get here. We know about normal two winding transformer. In the transformer there is a possibility to get step up or step down voltages, but here in auto transformer there is only possibility to get step down transfer. Some applications we are good using this for variable speed variable voltage applications to apply, like in speed controls to start the motors, etc. The auto transformer is having only one winding. A part of that winding will act as secondary winding or output voltage winding. Means auto transformer is having only high voltage winding. It means primary with the part of one winding will access another part. Means part of primary winding only maybe primary a part of primary winding will act as secondary. Now here both primary and secondary currents are electrically windings circuits. Primary and secondary circuits are both electrically and also magnetically coupled. Means here the EMF induced is by using conduction process and also by using induction process. And the transformation ratio of auto transformer is always less than 1. Auto transformer transformation ratio is always less than 1. Transformation ratio we define with secondary voltage by primary voltage, or N2 by N1 or I1 by it in terms of currents. So output is always step down voltage applications. That's why transformation ratio is always 1. The main only disadvantage of auto transformer is there is no electrical isolation. There is no electrical isolation between primary and secondary windings. There is a wire conduction, so isolation is not there as like a two winding transformer. The advantages of auto transformers are it has only one winding, hence we can say it requires low core material to accommodate winding. As LV and HV winding electrically same, no insulation is required between low voltage windings and high voltage winding terminals. So less insulation is required. As part of HV winding used as LV winding, so separate copper not required for windings in auto transformer compared to two winding transformers, compared to same rating of two winding transformer. Here size, weight and cost if we compare, auto transformers no doubt size is less. Why? Because only two windings we are using. Core required is also less compared to two winding transformer. That's why weight is also less. If both winding less required, core metal required less, means no doubt cost is also less of same rating of, if we compare the same rating of two winding transformer. If core required is less, means no doubt iron losses are also less. Core metal required less means iron losses or core losses also less. So for simple what we required for about auto transformers. Now come to three-phase transformers. Means up to now we discussed about single phase. One AC supply if given to primary, secondary you are getting single phase supply. Now to prepare three-phase supply, we need how many windings? No doubt we need 3 windings. If you take 3 windings, 3 single phase transformer banks, if you interconnect them, we can form 3-phase supply. Otherwise, by placing 3 windings inside, we can prepare 3-phase auto transformers. Means here there are also step up, step down output voltage, step up or step down voltage or currents are available. So if you taken 3 windings, you know how to prepare 3-phase. By connecting either star connection or delta connection. When star will form, if similar ends are connected at one point, star connection will forms. And if dissimilar ends are connected together, then delta connection forms. Delta connection provide a closed path for each winding. Right. The EMF equation, if you compare there, per phase only always we define voltage. And for single phase or three phase, see there E1 I represented with N1, E2 represented per phase is with N2 number of based on number of turns. And here line voltages are depends on type of connection, but phase voltages are same. Phase voltages are same. Just I was given definitions here for star connection and delta connections, and trans ratio N1 by N2 or E1 by E2, but transformation ratio is different, trans ratio is different. If your examiner is given a trans ratio as some 1:2 means N1 is N1, 2 is N2. Well, during analysis here, phase turns ratios has to be only considered here, any connection comparatively. Means here from primary to secondary, phase values only will shift. The phase value of voltage or phase value of current depends on connection. The line values will varies. Line values will varies. See, we are having only two connections: star star delta, star connection and delta connection. So we can get here four possibilities of connections. Delta delta means primary windings are connected in delta, secondary is also connected in delta. Similarly, star star, both primary secondary connected in star. Delta star transformer and star delta transformer. You know the relation in star connection, line voltage is equal to root 3 times the phase voltage, line currents are equal to phase currents. Here currents here in star connection currents are same way, because current will flow from one phase to another phase only. That's why there is no path for division of currents. You can say both are the windings are in series, which is having more positive from one phase to which is having more negative, current will flow. That's why through two windings current will flow, in another winding no current will flow at any instant of time. Delta connection, no, phase voltage equal to line voltage and line current is equal to root 3 times of phase current. First let us discuss about delta transformer connection. See there primary dissimilar. See I took 3 windings primary, 3 windings secondary. Dissimilar ends are connected, means any one phase R dash. Primary RP I specified, RP dash is that winding end, another end. So RP dash and YP connected, YP dash VP connected, VP dash RP connected. Next, from the common point we took wires. If you are given 3-phase supply, it comes under 3-phase delta connection. And same secondary windings also I took there 3 windings, dissimilar connected, delta connection is formed. Between those 2 windings parallel lines are represented, means between those 2 core material is there. Core is used for low frequency transfer, low frequency applications. Now see star connections here similar ends are connected here, primary side and secondary side. See the RP dash, YP dash, BP dash are connected at one point. So neutral will be available, we will take if you required. Another ends we take RYB. If you given 3-phase AC supply, primary represents star connection. Secondary side also when these are connected in star, you can get star connected output supply. Delta, this depends on applications, we will lose this connection. Next, delta star application. Primaries are connected in delta and secondaries are connected in star connection. Primaries are connected in delta and secondaries are connected in star connection. Means delta connection we discussed already definition. These similar ends are connected, primary side, secondary side, similar ends. And next about star to delta connection. See the connections windings, primary side star, if you given supply, it comes under primary. If you take a connected low terminals, it comes under secondary side. So one side star connection, another side delta connection. This is about 3-phase connections. Next, how those voltage and currents varies from primary side to secondary side, but different type of connections. This is important, we have to analyze. Here I assumed K, transformation ratio K is equal to V2 by V1, E2 by E1 or I1 by I2 or N2 by N1. Remember K is equal to V2 by V1 or I1 by I2 we assumed. Now come to star connection. Primary side is star, I'm assuming here phase voltage as V. Then what is line voltage? Now that star connection, line voltage equal to root 3 times of phase. That's why I wrote here line voltage equal to root 3 times of phase voltage. Now come to current. I assumed current in each phase current as I. Then what is line current? Because it's a star connection, so line current is also equal to I. Now those values are shifting to secondary side. See, primary voltage is V1. What is secondary voltage? Secondary voltage V2, K is equal to what? V2 by V1 we discussed. So primary voltage is V. Then what is secondary side voltage? V2 is equal to K times of V. See here, say phase voltage only will transfer as we discussed. So phase voltage we assumed secondary side, phase voltage is equal to K into V. Why? Because that V2 is equal to K into V1, K into primary voltage. So secondary side connection also star, hence what is the line voltage? Root 3 into K into V, root 3 into K into V. Here primary voltage we assumed as I phase. What is second? So primary current we assumed as I, phase current I. But a secondary current here, this transformation is reverse. I1 by it is equal to K. So I2 is equal to what? I1 by K. So we represented here I1 by K. Similarly, line current is equal to I1 by K or I by K. Simply we assumed I by K because currents are same in star connection. Now come to delta connection here. Phase voltage I assumed as V. So then what is line voltage? Line voltage also V. Now come to phase currents. Phase current I am going to assuming here I, connection is delta. So what is line current? Root 3 into I. Now come to secondary values. So voltage is always K times the primary voltage. So phase voltage there we assume V primary side, secondary side voltage is K into V. In delta connection, line voltage is equal to phase voltage. That's why line voltage also equal to K into V. Now primary side phase current I assumed as I. So shifting to secondary side, that I2 is equal to what? I by K. The connection is what? Delta connection. So line current is equal to what? Root 3 times of I by K. Root 3 times of I by K. Now come to delta star connections. Delta star connection. Primary side delta, secondary star. So primary side we phase phase voltage I assumed as V. Then line voltage also V. Why? Because delta connection. Here assuming phase current as I. Here assuming phase current as I, then line current is equal to root 3 times of I. Why? Because it's a delta connection. Now come to secondary side. Primary voltage V means secondary voltage is K into V. The connection is here, what connection we are using? Secondary side star connection. So line voltage is equal to root 3 times of phase voltage, which is equal to root 3 into K into V. Phase current we assumed here there as I primary side. So secondary side is I by K. The connection is what connection? Star connection. Line current is equal to phase current. Again I by K we can get. Now come to star delta connection. Primary side star, secondary side delta connection. Phase voltage we assume as V. Then the line voltage is root 3 times of V. Next phase current is I. Line current is also I. Now phase values are shifting. Phase voltage we assume V. Then what is phase voltage? Secondary side K into V. And what is line voltage? Here delta connection here. So line voltage equal to phase voltage. So K into V same we can get. Phase current we assume I there. Here phase current is I by K. The connection is what connection we are using? Delta connection. So line current is equal to root 3 into I into K. This is about how voltage and current magnitudes varies from different types of connections, and these connections we are going to using for different types of applications. Generally any transformer primary should be delta connection. Delta connection. Why? Because to reduce harmonics, to kill third harmonic components there, to get sinusoidal AC supply, to avoid flux, as sinusoidal flux should be peaky waveform. That we'll see in the next session. This is about auto transformer and three-phase transformer connections. Thank you very much.